field is 2 Tesla given. So we have to calculate the induced EMF. We have to calculate the induced EMF and the electrical power.
Yes, sir.
So induced EMF will be in the wire, and that induced EMF will be due to the motion of the wire. So basically we have to calculate the motional EMF, and the formula of the motional EMF is minus V into L into V. Okay,
Yes,
so
sir.
minus V is given as 2, length of the wire is 10, velocity is 5, so you will get this minus 100 volts. Okay, and mechanical power is spent. Mechanical power is spent. We have discussed power here. Here I have discussed the power. So
Yes,
this
sir.
is your mechanical power. V square L square V square by R. So this formula will be used. Okay, this
Yes,
formula
sir.
will be used here. So we can use this formula and we will get the answer. So mechanical power is equal to V square means 2 square, L square means 10 square, V square means 5 square divided by resistance is 5 ohm.
Yes,
So
sir.
finally, when you will calculate this, you will get 2000 watt. 2000 watt. Okay. This is a very simple question.
Yes.
Okay, note down.
Done, sir.
Okay, write down this.
Done, sir.
Okay, so we will discuss this. So before this, you should know what is the angular velocity. You should know.
Yes, sir.
I have told you omega in the when we were discussing the
Yeah,
one question,
yes.
one question related to that torque.
Yes,
So
sir.
again, I am telling. So what is omega? The concept of omega I am telling. So suppose this is the circular path, and suppose a body initially is at point A, okay, and finally this body is moved to the point B. In moving from A to B, the body swept an angle of theta, swept an angle of theta, and this theta is known as the angular displacement. This theta is known as the angular displacement. Suppose in going A to V, the body is taking a time t. T is the
Yes,
time.
sir.
So the angular velocity omega is given by theta divided by t. This thing you should know. And there is one more relation. On the circular path, when the body is moving, then there are two types of velocities. Means one is angular velocity and another is linear velocity. So suppose at this
Yes,
point I
sir.
want to find the linear velocity. So linear velocity will always be the tangential to that point. Linear velocity will be tangential to that point.
Point.
So there is the relation. Suppose r is the radius of this circle. So there is the relation between the linear velocity and angular velocity. V is equal to r omega. R is the radius of the circle.
Yes,
Omega
sir.
is the angular velocity. What is your omega? You can write here. Here you can write. Omega is your angular velocity. Okay. Now we will discuss this derivation. This derivation, if you know this concept, then it will be very, very easy for you. Just a moment. What? Why? I want to reduce the size, but why this is not working? Okay, no problem. So here, this is your wire AB. What is this AB? This AB
Wire.
is your wire. Remember, this AB is your wire. I have written here AB is your wire or your conductor. L is representing the length of the conductor. So this wire is rotating like this. In a circular path, the wire is rotating.
Yes, sir.
This is your wire and this wire is rotating. And there is one magnetic field, inward magnetic field. So basically you can say this wire is rotating in the inward magnetic field. Earlier what was the case? Your wire is moving linearly in the magnetic field. Now your wire is rotating in the magnetic field.
Yes,
So
sir.
we have to find the EMF across the ends of this conductor AB when this wire is moving in a plane which is perpendicular to the magnetic field. Here you can induced EMF across the ends of the conductor when the conductor is rotating in a plane perpendicular to the magnetic field. Okay, perpendicular to the magnetic field with an angular velocity omega. So this wire is rotating in this direction with an angular velocity omega. This is your angular velocity. Okay, this is your angular velocity omega. Now we want to calculate the EMF induced in this wire. So what we will do? First, we will calculate the induced EMF due to the rotation of a small element of this wire. So first I will take very small element of this wire. Very small element of this wire I will take. Suppose this is the element I have taken. Okay, this element I have taken,
Yes,
and
sir.
length of this element is dx. Dx is very small length of element of wire. Dx is
Very small element of length of wire.
small element of conductor. Small element of conductor, and this is at a distance x from the axis of rotation. What is b? B is a point from where the axis of rotation is passing. See here, like this. The condition is like this. Here, from here, there is one axis. Just a minute. I need one more pen. So now it's okay. This wire is rotating like this, now. So for rotation,
Yes,
there
sir.
is a need of one axis. So this wire is rotating like this, like this. So the axis will be like this. Okay. About this wire is rotating like this, so there will be one
Yes, sir.
axis. So about this axis, this is the axis, and
Yes.
about this axis, right? Wait. This is your axis. This is your axis, and about this axis, this wire is rotating like this. Now
Yes, sir.
understood?
Yes.
This thing should be clear. And there is one magnetic field in the along the y direction. Y direction is perpendicular to the length of the wire, because your length of the wire is along, you can say, in along the y axis. Okay. So magnetic field is perpendicular to the wire. Very good. This distance is x. This distance between this element dx and this v, and v is a point from where the axis of rotation is passed. Okay. Now, as this element is rotating, L is the length of wire. I have already told you, so no need of this. So we can write this dx here. So there will be some linear velocity of the wire as this wire is rotating like this. One thing you should remember. When something is rotating in a rotational motion,
Yes, sir.
angular velocity of all the points. This you can consider this pen is made up of n number of points.
Yes.
Infinite number of points. So all the
Yes.
points have the same angular velocity. Angular velocity is same for all the points. Why the
Yes.
angular velocity is same? Because if you can take any 2 points, that 2 point will swap equal in angle in equal interval of time. That is why angular velocity is same. Basically, you should know angular velocity for each and every point on the wire will be same. If I will take 1 point here, if I will take 1 point here, 1 point here, then angular velocity of both the point will be same, but the linear velocity will be different.
Different.
Okay. So at this point, suppose this is the linear velocity v. Suppose this is the linear velocity of this dx element. Okay, this is the linear velocity,
Yes, sir.
but angular velocity of this dx is same. Angular velocity of this
Yeah,
dx
the
is same,
dx is same.
and we know
Yes.
that v is equal to r omega.
Yes.
Okay, v is equal to r into
R
omega.
omega.
R this time is this distance will be r. V is equal to r omega. And what is r here? This x will be r. So v is equal to, you can write x into omega. You can write this, na? V is equal to x omega. So this is the velocity. Okay. So now in this small element dx, there will be the induced EMF. Suppose that induced EMF is given by dE. That dE is given by formula of induced EMF will be minus V into length into velocity.
Yes, sir.
So we have the magnetic field V. Okay, V is the magnetic field here. This is the magnetic field V in the inward direction. Length of the element will be dx, into velocity. Now you will put this value. This is minus b into dx. For velocity, you will put x into omega. So finally, you have minus b into omega into x into dx. This will be your dE. Now, this is the EMF induced for a small element of the wire. What is this dE?
Small
EMF induced.
EMF induced for a small element of work.
Yeah, EMF induced in a small element dx of wire. For calculating the total EMF in this wire, you will do the integration. So we will
Yes.
do the integration of this dE, and this will become integration of minus b omega x into dx. Now we will take the limits of x. So x is at this point b, the value of x is 0, and at this
Yes.
point a, the value of x will be L. Okay, so we will apply the limit 0 to L. So this dE will become E. Now constant term we will take out of the integration. This b omega is constant. So this will be taken out of the integration. Now we will do the integration of x dx. So integration of x dx, limit 0 to L, I have told you. This will become, you will increase one power of x, and this power you will write in the denominator, and then you will apply the limits.
Yes,
Okay.
sir.
Here it will become half. This is L square minus 0. This will become half of L square. Now you will put this value here. This is minus b omega, and this is L square divided by 2. So this is the EMF induced in the wire. EMF induced in the conductor.
Yes.
EMF induced in the conductor. This is the EMF induced in the conductor. Now, this formula you should know, minus b omega L square by 2. This will be the EMF induced when one conductor is rotating in a magnetic field. So on this I have one question. No, it's fine. And okay, we will solve one question on the same formula.
On R omega.
Yeah, on this same concept, we will do one question.
Okay.
I'm writing the question. So the question is, I have to write the question this time. A wire of length 2 meter, of length 2
meters.
meter, is rotating with an angular velocity with an angular velocity 5 radian per second. 5 radian per second in uniform magnetic field. In uniform magnetic field of 10 Tesla. Calculate EMF induced. Calculate EMF induced across ends of wire. Across ends of wire. So same formula you will apply here. EMF induced across ends of wire minus b omega L square by So omega, what is the value of V is 10 Tesla.
Yes, sir.
What is omega? 5 radian per second.
5 radian per second.
Length of the wire is 2
2
meters. So this will
meters.
become 2 square
2
divided
to
by 2.
by 2.
So it will become 100
Yes,
volts.
sir.
It will become 100 volts. Now you can note down this and that question.
Okay. Done, sir.
Done? Okay. Just a minute.
Second scroll down.
Okay.
Done, sir.
Okay, so this is the uh, EMF induced when your first what we have studied, when the wire is doing the linear motion, what will be the
Yes, sir.
EMF induced. Now we have discussed when the wire is rotating, what will be the EMF induced. Now there is one more term here, mutual inductance. Okay, mutual inductance. So this is a little bit, not little bit different, means from the concept of the magnetic flux, this will be understood. Okay.
Yes,
So
sir.
I have told you what is the Faraday law. I have told you what
Yeah,
is the
yeah.
Lenz law and all that. So we will use all these things to explain the mutual inductance induction. So basically, I have two coils. This is one coil and this is another coil. Now this is one coil and this is another coil. This is one coil. This is another coil. This coil is connected with battery. Okay, and this coil 2 is connected with what is this? Harsh, tell me what is this? G?
Sir, 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 galvanometer, right?
Yeah, galvanometer. Very good. What is the use of the galvanometer? To
Sir, it is
detect the
used to
current.
detect feeble current.
Yeah, to detect the current. See, you will see the magic this time. Now, what I am doing, uh, I have just connected the key and I have just closed the circuit. When I have closed this circuit, so it is found that there will be some deflection in the galvanometer. Is this magic or not? This is a type of magic, I think. But what is the reason behind that? That we will study. So you are just closing the switch here and you are getting the current in this coil. Okay, so what is happening? See, when you will close this switch, when you will close this switch, so what will happen? Current will start flowing in this. Suppose this is coil I1, so I1 current is start increasing. So suddenly the current will start increasing from 0 to some value. When you will close this switch, the current will start increasing. Now, same concept. Current will start increasing. So this is a coil having current. So this coil will produce the magnetic field. This coil, Harsh, will this coil produce a magnetic field or not? Because this coil is carrying a current.
Yes, sir. It will produce because the key is closed.
Yeah, key is closed. This is sub I1. I1 is the current in this coil. So this
Yes,
coil
sir.
will produce the magnetic field, and I am saying that magnetic field is V1. What is V1? V1 is the magnetic field due to this coil. 1. And the effect of this magnetic field will be on this coil also. Okay.
Yes, sir.
Actually, magnetic field. There is the magnetic field. So this coil is also in the magnetic field produced by this coil.
Yes, sir.
Okay. Now this thing is clear. This thing is clear. Means this thing you should know. This coil is in the magnetic field of coil number 1.
Coil 1, yes.
Coil 1. Okay. Now, what will happen? We know that magnetic flux is directly proportional to the magnetic field.
Yes, sir.
Okay. Now, this thing will be used. So, when just you have closed the switch, magnetic field here will increase. Means magnetic field produced by the coil will increase. So you can say by increasing the magnetic flux, and the effect of magnetic field due to coil 1 is here also. So you can say when the switch is closed, so here you can say the magnetic field will increase.
Yes, sir.
Here also the magnetic field increase because there is some effect of magnetic field due to the coil 1 on coil 2. So here you can say the magnetic field will increase. Due to increase in magnetic field, what will happen? Due to increase in magnetic field, your magnetic flux will increase on coil 2.
Yes, sir.
On coil 2. So what you will say? Magnetic flux for the second coil is directly proportional to the magnetic field due to the coil 1.
Yes, sir.
Okay. Or we can say this magnetic flux is directly proportional to the current in the coil 1 because this magnetic field is directly proportional to the current. Okay. This thing you should know. This thing is important. Okay. Now when you will remove this proportionality sign, you will get one coefficient of mutual induction. This is the formula. And what is M? M will be your coefficient of mutual induction. Coefficient of mutual induction. So for the explanation, I have written here. And tell me, when the magnetic flux is increasing, as current I1 is increasing, na? This current I1 is increasing in this coil. Magnetic flux in this coil is increasing. So there will be one induced current here. There will be one induced current in this circuit. So that is why there is deflection in the galvanometer. So you can write the explanation whenever current in one coil change, EMF is induced in the neighboring coil. Okay, here there will be the induced EMF because there is a change in the magnetic flux. Due to the induced EMF, there will be the induced current. Okay, so whenever current in one coil is changed, EMF is induced in the neighboring coil. Due to the change in the current in coil 1, flux linked with the coil 2 will change. EMF will induce in coil 2 and hence induced current. current will be there in coil number 2. Okay, so this is the mutual process of induction, mutual induction.
Yes, sir.
So you can just a minute. You can note down this. Okay, you can note down this and
Okay.
this explanation also. I am just zooming it. Harsh, got it? What is happening
Yes, sir.
here?
Yes, yes, sir. Yes, sir.
Actually, this phenomena is related. Actually, both the coils are just related to each other.
Yeah, yeah.
If you will increase the current in this coil, so there will be current in this coil also.
Yes. So can scroll down.
Hmm. In transformer, there is a phenomena mutual induction.
Yes, sir. Yes. Sir, how many more topics are left in this chapter?
How many
More
topics?
topics. Yeah, yeah.
Just after that, there is one more topic, self-inductor.
Yeah, sir, sir.
Maybe I
After
think
that,
maybe this chapter will be finished today. Maybe there is one topic, eddy current, but that is removed from your
yeah.
syllabus, so we will not discuss that. There
Done,
is
sir.
one. Okay. So write down this also. This coefficient of mutual induction na, depends
Yes, sir.
upon the separation between the coil orientation geometry and this.
Yes, sir. Yes, sir. I'll
Just
write.
you can write down this also. So we will not waste time in this. So most probably today, I think this will be finished. Actually, I am having a class at 9, na?
Yes.
So maybe today we are not able to finish this, but we will try. I think there is one topic, self-inductance is left. After one derivation we have done.
Done, sir.
Okay. Now write this also 1 Henry, and I have not written the unit of this. So unit of this coefficient of mutual inductance is Henry. Okay.
Henry.
So 1 Henry is defined by. Just a minute. First we will do the derivation, then we will write.
Okay.
We will do the derivation, then we will. Okay. So here we know that we can write. We can write in general flux in one coil is directly proportional
Yes,
to the current in another coil, and that phi is equal to mi we have. Okay, phi is equal to mi we have. So now we will use Faraday law, that is E is equal to minus d phi by dt.
yes, sir.
So we will put this value minus dy by dt. We will put the value of phi here, mi. Okay, so this coefficient of mutual induction will be come out of the differentiation. Then here we
Yes,
will
sir.
have di by dt minus m di by dt. Okay, so now SI unit, what is the SI unit of m? SI unit of m. So for the SI unit of m, what you will do? Calculate m from here. You will get m is equal to e dt divided by di.
Yes, sir.
So this will become unit. I am talking about the unit volt second by ampere, and this unit is known as the Henry. This unit is known as the Henry. When you will calculate 1 Henry, so you will put 1 EMF for 1 second and for 1 ampere current. You will put and you will get 1 Henry. So this is the definition of 1 Henry I have written here. So you can note down this. So here the flux linked with the coil number second is directly proportional to the current in coil 1. When is your exam?
Of physics?
Yeah, means you are
On
saying you were
6th. 6th.
on 6th. So are you available today? Not today, tomorrow for half an hour.
Yeah, tomorrow I'm available, sir.
Hmm?
Yes.
So if today is not finished, then tomorrow in half an hour I will finish this chapter.
Okay, sir.
If I will not have the class at 9 according to me, then today I will finish. Otherwise, I will take half an hour tomorrow and I will finish this chapter.
Okay.
Definitely. Yeah.
Sir, I'm writing this, right?
Yeah. Okay. You should write this, right.
Yeah.
Acha, tell me what is this small e is representing?
EMF.
Fine.
Done, sir.
Done. Okay.
Yes.
So 1 Henry, when you will define the 1 Henry, so you will put EMF value 1, this di by dt is equal to 1, then you will get the 1 Henry. Okay. So
Yes, sir.
this is the definition of 1 Henry. You can write.
Okay.
Like
Yes,
we
sir.
have defined the 1 Coulomb, we have defined
Yeah.
1 Newton. So like you can define the 1 Henry. If the rate of change of current of 1 ampere per second induce an EMF of 1 volt, then mutual induction of the coil is 1 Henry. Henry is a unit of mutual induction, coefficient of
Yes,
mutual
sir.
induction. Okay. And right.
Done, sir.
Done. Okay. So we will discuss this now. We will have two solenoids.
Yes.
Okay, we will have two solenoids, and those two solenoids will be coaxial. Coaxial means
Yes.
one solenoid is like this, another
Yeah.
solenoid will be on that.
On top
Okay,
of it. Yeah.
so yeah, this white color solenoid is there, and this yellow color solenoid we have.
Yes, sir.
So I have just marked this white color solenoid as solenoid 1. So this
Yes, sir.
solenoid, white color solenoid, have the radius R1 and length L. Here length of both the solenoids are equal. Okay,
Yes, sir.
length of both equal. So R1 is the radius for one, L is the length. N1, what is N1 is very much important. N1 is the number of turns per unit length of the solenoid. And I have written here number of turns per unit length of the solenoid.
Yes,
There is
sir.
one more term, capital N. Capital N is total number of turns. Capital N is total number of turns. This is 1 turn, 2 turn, 3, 4,
Yes, sir.
5, 6, like this. So total number of turns, or you can say total number of coil. So this, you can see this as a circular coil. 1 turn means 1 circular coil. And we know that the magnetic field due to the solenoid will be mu naught Ni.
Yes, sir.
We have derived this now.
Yes, sir. Yes.
Okay. So this thing will be used. This derivation will be finished most early in 15 minutes. We'll finish this. Okay. So coefficient of mutual induction we have to find for a pair of two long solenoids of equal length placed one inside another. Means this yellow color is inside the white color solenoid.
Yes, sir.
Okay, so first, what is the thing? This current I1 is flowing. Suppose initially the current I1 is flowing in this white color solenoid. This is bigger solenoid now. This is bigger solenoid.
Yes, sir.
Okay, because this yellow color solenoid, the radius is R2, length is L, and number of turns per unit length is N2. So you can say
Yes, sir.
your R1 is greater than R2. So there is the current in this solenoid, white color solenoid. So what will happen? What will happen? There will be the current in the white color solenoid.
Yes, sir.
So due to the current in the solenoid, there will be the magnetic field.
Yes, sir.
Okay. Now keep this picture in your mind. Okay, keep this
Okay.
picture in your mind.
Okay.
Okay, so here you can take I1 current in solenoid number 1. So magnetic field due to the solenoid 1, suppose V1 is the magnetic field due to solenoid 1. So you can write magnetic field due to solenoid 1. Harsh, are you getting
Yes,
or
sir.
not?
Yes, sir. Yes, sir.
See, actually this is the only white color solenoid.
Yeah.
So this white color solenoid, there is a current in the solenoid, and I have
Yes,
told you
sir.
when due to the solenoid, the magnetic field when there is a current is
It's
mu
produced.
naught
Yeah.
Ni. Okay. So
Yes.
okay, very good. So magnetic field due to the first solenoid will be mu naught and
Ni.
N1 and N1. We will Ni, you are right, but we will take N1
Okay.
because
Yeah.
we are taking the magnetic field for solenoid number
For
1.
you. Oh yeah. Sorry. One.
Okay, mu naught N1 I1. So this will be the magnetic field due to the solenoid 1, and this magnetic field is inside the solenoid. Okay,
Yes, sir.
so you can write magnetic field due to the solenoid 1 and write here inside. Now this thing is finished. Now you can see that at if I will say this current is changing. This current is changing. I am
Change.
writing here this I1 is changing. Changing means either increasing or decreasing. So what will
Decreasing.
happen
Yeah.
when this current will change? When this current will change, suppose current is increasing. So this current will increase. So magnetic field will increase.
Yes, sir.
Magnetic field will increase now.
Yes,
So
sir.
you can see this yellow color solenoid is in the magnetic field of white color solenoid.
Yes.
So when magnetic field will increase due to this white color solenoid, so you can say there will be increase in the magnetic flux linked with the yellow color solenoid.
Yes, sir.
Confusing or
Kind of.
means, are you getting or not?
Yeah, yeah, I'm getting it.
Okay, just a minute, I'm just explaining once again. First write the formula of the magnetic flux. magnetic flux Magnetic flux in the second coil. Magnetic flux in the second coil will be the magnetic field in which the coil is, means second coil, your second coil. This second coil means this yellow color coil is in the magnetic field of white color coil. So you will write
Yes,
here
sir.
V1. There will be some area of second coil because we are
Yes, sir.
calculating. Okay, now cos theta. What is phi 2? Phi 2 is flux linked with coil 2, or you can say solenoid 2.
Yes, sir.
You can write here coil 2 because we are
Call
just
to right.
calculate. We are initially we are calculating for one coil only. Flux linked
Yes,
with
sir.
coil 2. Okay, this is the thing. So now what will be the theta? We know that the magnetic field due to the solenoid is axial.
Yes, sir.
Okay, now take any one of the coil. Suppose this is your coil. So in this coil, when you will take the area vector, so area vector will also be axial. So this
Yes, sir.
theta will be 0 degree. So you can write phi 2 will be V1 into A2. What is V1? Mu naught
Magnetic field one. Yeah.
mu naught N1
N1.
N1 into I1. What is
I1,
A2?
yeah.
A2 A2 is the area of this coil. This coil is
Yes, sir.
circular. I am just
Yes, sir.
talking about one coil. This
Yes,
coil is
sir.
circular, so we will take pi R2
Two,
square.
yeah, pi area,
Pi
sir.
R, yeah, area
Yeah.
circular area,
Yeah,
na?
pi
This
r
is
square.
circular.
Yeah, pi r square. Yes.
So what is this? You can write phi 2 as the flux linked with each coil of solenoid 2.
Yes, sir.
This is the phi 2. What is phi 2? Phi 2 is the flux linked with
Flux
one
ring
coil.
the coil. Yeah. Yes,
Linked
sir.
with one coil. Okay. And now see. Total number of what are the total number of coil? How we can calculate the total number of coil? So total number of coil in of the solenoid is capital N,
Yes, sir.
and there is a relation between the capital N and small n. Okay, so just tell me, this phi 2 means, here I can write here also. This is the flux for one coil. This is the flux for one
Flux
coil.
for one coil.
For,
Yes, sir.
for n coil, n coil, the flux will be multiplied by n,
Yes, sir.
and this term multiplied by n, and phi 2 means mu 0 n1 I1 and pi of R2 square. Means what I have done, I have multiplied this term with n. With n I have multiplied this
Yes,
term.
sir.
So what I get? Total flux of this yellow color coil, or coil number 2. Total flux linked with coil number 2.
Number 2.
Are you getting or not?
Yes, sir. Yes, sir.
Okay, fine. Now I have written there small n is equal to capital N by L. So from here I can calculate capital N, that is small n into L. And L of 2 we will take, and same, L is same. Okay, L is same. Again I am writing number of turn for the coil 2. Actually this is a flux for coil 2 na. This will be
Yes.
N2. This will be N2. Number of means magnetic flux for the coil 2. Magnetic flux for the coil 2. So we will take the number of turns, total number of turns in the coil 2. So total number of turns in the coil 2 given by the N2 divided by L. So you can calculate from here, and okay, this will be your small n2, number of turn per unit length of coil 2. This will be your n. Okay, this will be your n. So
Yes, sir. Yes, sir.
you can calculate n from here. Your n will be n2 into L. Are you getting or not? Means this
Yes,
thing.
sir. Yes.
I have taken this n2 because I am calculating the flux, total flux for this coil n2.
Yes.
Okay. Now this is the phi 2, and this n2 can be written as small n2 into
Small
L.
N2. Yeah.
This is mu naught
Mu naught.
n1
N1 and I1.
I1, and this is pi. This is R2
R
square.
square.
R2 square. Now phi 2 can be written as you can write phi 2 as this n1 into n2,
Yes.
and you can write before that mu naught. You can write mu naught n1 n2. So this is mu naught, this is n1, this is n2, this is
Into
L, this is
I1.
pi R2 square, and this is I1.
Yeah, I1. Yes.
and I have told you phi2 is equal to coefficient of mutual induction into
Mutual
I1
inductance. Yes, sir.
into I1. So now suppose this is your equation number 1, this is your equation number 2. Now compare both the equations. So you will get the coefficient of mutual induction, this thing, this part you
Yes, sir.
will get. That is
Yeah,
mu
we can
0
I1
N1 N2 L
L
pi
pi R2
R2
square
square.
square.
So this is your coefficient of mutual induction you
Mutual
will get.
inductance.
Mu naught N1 N2 pi R means L into pi R square. See here, I have told you this thing. Phi2 is equal to m times of I1.
Yes, sir.
So this thing we get. Okay, so now you can note down this.
Okay.
I have written here also that angle between the magnetic field and area vector is 0.
Yes, sir.
And m is the coefficient of mutual induction. Means you can say, okay, this is already written. So last topic is left, that is self-inductance.
Yes. So can you scroll down? You can scroll down.
So Harsh, one topic will be left, that is self-inductance,
Okay.
self-inductance, and after then
Yes,
that
sir.
eddy currents. So have your
This
teacher,
that's deleted, right?
have your teacher done in your class, that chapter, that
No, sir.
topic?
No.
No, na?
No, sir.
So
No.
we
No
will not
notification.
touch, that topic. So self-inductance
Okay.
is very small topic. It can be finished in 20 to 25 minutes. Okay.
Yes, sir.
So
Okay.
if you are available for half an hour tomorrow or 20 minutes for tomorrow, then we can finish that.
Yes, sir. I'm available, sir. You can keep the class at the same time. Like,
Same time, same time.
yeah, same time. Yeah, like
Okay.
7:30
So
for you.
so don't think that this chapter is not completed. But this
No, sir.
chapter is
No, sir.
this chapter is
Yeah, it's
95
completed. I know.
95% completed. But there are
Yes.
some things, means you have to focus, that you have to revise the notes. Okay. You have
Yes, sir.
to solve some questions, some previous year question, then you will get through the concept more clearly. Okay.
Yes, sir.
So this thing you have to follow. From my side, I think this chapter is completed, but one thing is left, that is self inductance. Okay. And
Yes, sir. Done, sir. Done.
okay, so self inductance, I think we should discuss that in the next tomorrow class.
Yes, sir.
Okay. So remember this this derivation
Yes, sir.
may be appear in your exam. So what you
Yeah.
will do there? They are two coaxial coils. Coils means, what is the meaning of the coils?
Solenoid.
Solenoid and
Round,
coil.
round. Yeah, round wire.
Yeah, not coil. They are two coaxial, and you are changing current I1. You
Yes,
are
sir.
changing current I1 in one coil. So there will be the induced current in another coil due to the mutual induction.
Mutual
Okay.
induction. Yes.
So you can write, the current is changing. You can write I1 is the current in the solenoid, and that current is changing.
Changing.
You can add here. You can add here this.
Done. Yes, sir. Done, sir.
Done.
Yes.
Okay. So now we will meet in the next class, or maybe
Tomorrow.
tomorrow we will have a
Yes, sir.
class. Okay.